Okay, so let's remember what we're doing. We're talking about, what are we talking about? Can anybody remind us what we're talking about? Elizabeth.
Error
of what?
Like when you take the sequence to a certain amount of points.
What sequence? Can anybody sort of like roughly tell us what we're doing? It's maybe more precisely than that, but still kind of roughly. What are we doing? We have some function, and then we create this other thing. This other thing is what? Yeah, Mira.
Is it like find the error between a function and the Taylor sequence to a certain like n?
Yeah. So you start off with some function, okay, and then so this function is c infinity on some interval centered at some point, okay, and and then you create this thing called the Taylor series, right? Right, the Taylor series. So the Taylor series is the sum of the kth derivative evaluated in a over k factorial x minus a to the k. K goes from 0 to infinity, right? And so this thing is a power series, right? This thing is a power series in x minus a, and it's basically like a polynomial approximation. I mean, if this were centered at, if we were doing, it's easier to think about this at 0, so I often just do it at 0. So c centered, c infinity on, say, then the Taylor series centered at 0. Centered at 0 is, you take you just let a be 0, right? X to the k goes from 0 to infinity, right? So this is very clearly just some sort of infinite polynomial, and so you've got your function and you're trying to approximate it with an infinite polynomial. You're trying to say my function is an infinite polynomial, okay? And that may or may not be true, right? Okay, so so the question is, does this thing converge back to this, right? Does this thing converge back to this? That's the same question as, does the sequence of partial sums converge back to this, right? That's what it means for an infinite series to equal something. It means that the sequence of partial sums converges back to that thing, right? So you look at the sequence of partial sums. Well, the partial sums are the sums from k equals 0 to some fixed value, right? To some n. Right? So the partial sums are these things called the Taylor polynomials. Right? We sum from k equals 0 to n, just you take the sum of the first n plus 1 terms. Okay. This would be called the nth Taylor polynomial. Right? And so your question is, does, right, let's call this thing p sub n. The question is, does p sub n converge to f of x? Right? Does p sub n converge to f of x? Right? Does the Taylor? That's the same question. Does the Taylor series converge back to the function? Okay. And so what we were saying was that, yeah. And Elizabeth, I'm glad that you had the guts to try to give an answer. That's good. Yeah. So I mean, right, it's sort of like I probably told you the story about shamelessness. Did I tell you this? Right? No. So as I get older, I get more and more confused. I forget which class I've spoken to. Next semester, I probably will look at you and say, "What's your name?" Yeah, I bet it sounds like a joke, but it's actually true. Like I've seen students from my last semester, and where like 10 years ago, I had a memory that I'd say, "Oh yeah, Mike Rosman, yeah, I taught you in Chicago in such and such a year." But now my memory, even after one semester, I forget people's names. It's pretty horrible getting older. Yeah. So learn as much as you can while you're young and you have a good memory and your brain is flexible. don't waste your time making friends, dating, this other stuff, right? Just, right? You can do that later when your brain is stiff. Okay. While you're young, pack your brain with as much information as possible. That's my advice to you. Okay, because it just gets harder as time goes on. Now I don't even remember what I was talking about. What was I talking about? Oh yeah, right. The story, right? So yeah. Okay, so my Chinese teacher in college said to us, the key to learning is shamelessness. Right, shamelessness. You don't want to be embarrassed about anything that you say while you're learning something. Right, anything that you think. You just try it and then see if it's right or wrong. Right, and this is sort of like how babies learn. Right, they say all sorts of crazy things and then you correct them. Right, so and that way you learn quickly. Right, but if you don't try, then if you don't sort of venture some ill-formed sentence or ill-formed mathematical idea, then you won't be corrected and you won't be able to form ideas, basically. So you want to be able to talk about mathematics. You want to be able to talk about it. Okay. In any case, we have this theorem that says that under certain conditions, the remainder, so if f has n plus 1 continuous derivatives in a neighborhood I of a point A, right? Then, so the picture is, here's some point A, and then there's some interval I around it. Okay, and you have some function, right? You have some function, and it's smooth on that interval. Okay, then for each point in the interval, right? So you choose some point in the interval, and you're wondering, right? How good is my approximation at that point? So, right, you choose your point, you choose your interval there, and you evaluate p sub n, right? And you're wondering how bad is p sub n? Right? Does p sub n basically give you back f of x or not? Okay. And so the Lagrange remainder formula says that. Anna.
Oh, I just can't read what you say in a
Neighborhood. Sorry.
Neighborhood.
Yeah, neighborhood. It just means an interval, an open interval I containing that point A. Then for each point in the interval, the error equals the n plus 1th derivative evaluated at some point c over n plus 1 factorial x minus a to the n plus 1 for some c between x and a. Right, so this thing, the remainder, we mean the difference between the function and the approximation. Okay, so that was the Lagrange Remainder Theorem. Okay, that's the Lagrange Remainder Theorem. Okay, and so let's do a couple of examples of this. Okay, does the statement make sense? Right? It says that if you're trying to approximate your function with the nth Taylor polynomial, then there's some point in here, I don't know where it is, there's some point between a and x where the n plus 1th derivative of f at that point divided by n plus 1 factorial times x minus a to the n plus 1 is the error. The error looks like this. Okay, the error looks like this for some point between a and x. Okay, we're not going to prove it. Sorry. Right. So remark. If we can show that Rn x, the limit of Rn x as n goes to infinity is 0, we know that Pn x goes to f of x. Right? In other words, your function is recovered by the infinite series. This is going to be the use, right? If we can show that this remainder goes to 0, then our goal is achieved, right? Our power series, our Taylor series actually does give you back your function. Okay. Okay. So let's see how we do that. Okay. So the simplest example is where f of x is e to the x. And one of the most simple examples is this. Okay? Okay, so this thing has, so notice e to the x has, is infinitely differentiable on the whole line. Right? So we can use this theorem for any n. Right? We can go the full series basically. Okay. So we're going to take the Taylor series around 0. We're going to take the Taylor series around 0. We don't have to. We could take it somewhere else, but let's just take it around 0 for simplicity. Okay. So you know that the Taylor series for this guy is summation 1 over k factorial x to the k equals 0 to infinity. Right? Because you get the kth derivative evaluated at 0 over k factorial times x to the k. But the kth derivative of e to the x is e to the x, and you evaluate that at 0, you get 1. Okay? Okay. So we're wondering, how good is the whatever Taylor approximation? And we see that, so suppose this is 0, and we're taking some point x, right? Lagrange says that the error, equals the error equals e to the c over n plus 1 factorial times x to the n plus 1. Okay, right? That's what Lagrange's theorem says, right? Right. Lagrange's theorem says the arrow is going to look like this, right? For some c between 0 and x. Okay. Well, so for some c between 0 and x. Okay. So how big could e to the c be? How big could e to the c be? Well, we have a control on it. At biggest, it's e to the x, right? So we know that, right, e to the c is less than e to the x. Okay, that's actually a lie. That's actually a lie. Okay, so I lied to you, but let me tell you why. The trouble is that x could be negative, right? Suppose x is over here, then your c would be between 0 and x, right? In that case, your e to the c is less than, not e to the x, but less than e to the 0, right? Everybody see that? Right? If x is positive, then e to the c is less than e to the x. But if x is negative, then e to the c is less than 0. E to the 0, namely 1. Okay, is that all right? Everybody, now I'm telling you the truth. Okay, so e to the c is less than the larger of e to the 0 and e to the x. Okay, right? Whichever one is bigger, that will give us a bound. Right? What's called, right? If x is negative, right? If x is negative, you get this guy. If x is positive, then it's this guy, right? If e to the c is going to be smaller than this guy, or it's going to be smaller than this guy. So it's going to be smaller than the larger of those two. No matter what x we choose, it's going to be smaller than the larger of those two. Okay. Right. Right. It's like saying half of you are smaller than this, and the other half are smaller than this. Right. So all of you are smaller than the larger of this. Right. That's all we're saying here. Okay. Call that number n. Call it n, whatever it is. So now, e to the c is smaller than this number m, and so Rnx is smaller than, if we look at the absolute value of Rnx, that's smaller than m over n plus 1 factorial x to the n plus 1 in absolute value. Right? Okay. But the limit of m over n plus 1 factorial x to the n plus 1 as n goes to infinity is what? You've got some number raised to the n plus 1th power. You're dividing by n plus 1 factorial. And you let n go to infinity. What's gonna happen? 0, right? You get 0, right? Because this x is some fixed number, right? This x, maybe x is 10. Well, you got 10 to the n plus 1, but over n plus 1 factorial, and the n is becoming infinitely large, right? right? You're going to be multiplying by tens, but you're going to be dividing by larger and larger numbers, right, as you go on. Okay, and so the limit is going to be 0. Okay. Okay, so that tells you that the limit of the remainders is 0 as n goes to infinity. Okay, so the remainders go to 0, and so right. So in fact, f of x does equal summation x to the n over n factorial as n goes from 0 to infinity. Right? The power series, sorry, e to the x actually does equal its power series.
M is larger.
M was the larger of e to the 0 and e to the x. Okay, any questions on this? Right. So this is how you use the Lagrange the Lagrange Remainder Theorem to show that the power series, the Taylor series, actually does return you your function. Okay, right. Okay. Maybe let's do another example. So maybe this example is simpler. F of x is sine of x. Okay, and recall that the Taylor series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus et cetera, et cetera. Okay, so our question is, does the remainder go to 0? And Lagrange says, well, our remainder is going to be, right, the n plus 1th derivative evaluated at some point c over n plus 1 factorial times x to the n plus 1. Okay, I'm going to put absolute values on everything. Because we're just trying to show that this thing goes to 0. As long as the absolute value of it goes to 0, it goes to 0. Okay, so what can you tell me about the absolute value of the derivatives of the sine? What kind of control do you have on the absolute value of the derivatives of the sine? How big can they be? Can I get 2? I can do it.
As long as it's between 0 and 1.
Between 0 and 1, exactly, right? Right? The absolute values are sine or cosine, or they're plus or minus sine or cosine, right? All those things in absolute value are smaller than 1, right? So I know that this thing is smaller than 1 over n plus 1 factorial. Right? Because this thing is smaller than 1. Smaller than or equal to 1. Okay, and then as n goes to infinity, what happens to the remainder? Well, same thing as before, right? Just by the same reasoning as before. Over there we had an m, here we have a 1. Okay, your m is 1 here. Okay, again, the remainder goes to 0, right? And so we know that the Taylor series for the sine actually does give you back the sine function. Everybody see, getting an idea of how to use the Taylor formula? It's basically try to get some control on the size of the derivative. Right? If you can get some control on the size of the derivative, right? It's smaller than 1,000, say. Well, then your remainder is going to go to 0. Okay. So that's the idea of the formula, right? And once we have that formula, the cosine formula also follows just by differentiating, right? Because we would know that the sine equals this on the whole line, and then we had that theorem earlier that says if you differentiate a function, you just differentiate termwise, and it's still valid on the same radius of convergence. Well, that's going to be the whole line again. Okay, so this is how you use the theorem to show that the series converges. Okay, right? How to use Lagrange to show the series converges. The Taylor series. I shouldn't say converges, but it converges, recovers the function. In other words, it converges to the function. Converges to the function. Okay. As a bonus, we also get this game of error estimation. Right, so along the way, we also, this is just like a side comment. Along the way, you also get some estimates on the size of the error. So, for example, what is the sine of the number 1? Okay, so suppose you want, say you want the sine of 1 up to within 0.1, right? You'd like to know what the sine of 1 is within 0.1. Okay. Okay. Say, well, I know that the remainder, we just saw that the remainder is smaller than 1 over n plus 1 factorial. Right? We just saw that the remainder is smaller than x, the opposite line of x to the n plus 1 over n plus 1 factorial. Right? So you got this 1 over n plus 1 factorial. Right? Right? Our remainder, our error was smaller than this. So when I'm letting x equal to 1, I get 1 over n plus 1 factorial. Right? I feel like I've lost everybody somewhere. Like everybody suddenly became lost. Hannah.
What did it say of like the estimation? Something like
Error estimation.
Error
estimation. Okay. So again, let me start over. Right. We're trying to figure out what the sine of 1 is. We'd like to know what the sine of 1 is within 0.1 error. Okay. So we say, okay, we're going to use the Taylor series. Right. The Taylor series says that it's going to be 1 minus 1 over 3 factorial plus 1 over 5 factorial plus minus 1 over 7 factorial plus minus blah, blah, blah. Okay? And we're wondering, how far out do we have to go to be within 0.1? Right? How far out? This is eventually going to converge to the sine of 1, but you know, how far out do we have to go to be within 0.1 of the actual sine? We say, okay, well, the error by our calculation there, right, is going to be 1 over n plus 1 factorial. Right? So you say, well, look, if n equals 3, then the error is smaller than 1 over 4 factorial. Right? If n equals 3, the error is smaller than 1 over 4 factorial, which is something like 0.0416666666. So what that says is that we only have to go out to the power 3 term. Right? We only have to go out to the power 3 term. In other words, 1 minus 1 over 3 factorial is already within 0.1 of the actual sign. Right? So 1 minus 1 over 3 factorial equals, is about sine of 1 with a maximum error of 0.0416. Okay, which is great, right? We're already pretty close to the actual sign, even just by taking these first two terms. Yes?
So how did you directly choose n equals to 3?
I chose n equals to 3 because what I chose the first one that would give me something smaller than 0.1.
So it was a guess.
Well, you just plug them in, right? You just plug them in. You say, well, how far do I need to go out? N equals 2. Well, that would be 1 over 2. That's 0.5. That's not good enough, right? Let's try 1 over 3. Well, 1 over 3, I'm sorry, n equals 3 would be 1 over 4 factorial. Oh, that is good enough. Okay, let's stop there.
So this is like the question that we can get on the phone.
Yes. Yeah, everything up to today is fair game to the final. Okay. Okay, so another example. So, just along the same lines, if I said, I want you to be, to give me the sign up to 0.01 with an error of 0.01. Well, you would just start plugging in numbers, right, and say, maybe you try n equals 4, right, and you have 5 factorial here, right? But you see that 5 factorial is going to be good enough, right, because you're going to divide this by 5, right? You're going to divide this by 5. That's going to be smaller than 0.01. You get 0.008 something. Okay, and so if you go into the fourth term, that's kind of interesting because there is no fourth term, right? So we just take, right? There is no, the fourth term is 0 anyway. So actually, the first this is already good. This is already good to 0.001. I mean 0.01. Okay. So in any case, you see. I hope you see how it goes, right? Like somebody says, I want you to be within this with this error, and you just use the error estimate and say how big of an n do I need? That's not the most interesting. That's not the more interesting part. The more interesting part is this part over here now. Okay, this is just sort of a consequence. Anna.
So because n equal 4 does not exist,
Yeah.
you say n equal 3 is good enough.
N equals 3 is good enough, right? Because in between here are these 0 terms, right? That's 0 plus x plus 0x squared minus x cubed over 3 factorial plus 0x to the 4th, blah blah blah. So this says that you can go out to the 4th term. Well, the 4th term is just 0 anyway, so we're just taking the three terms. Yeah, Matt.
If the fourth term is 0, then why did you do one, like, and if n equals 4, 1 over 5 factorial?
So I was trying to find how far out do we need to go to make the error smaller than 0.01, right? And we have this formula for how big the error is, right? And it says, and if we plug it in, we see that the error is smaller than 0.01 once we get to 4.
N equals 4.
N equals 4, right? Once we get to the 4th term, the theorem says you're within 0.01. Okay, so now there is no 4th term, so what the theorem is telling us is that actually the first three terms are good enough. Okay. Don't make it complicated. So it says, the theorem says, if you want to, so somebody says you want to stay within 0.01, and the theorem says, okay, the error is smaller than this. Okay, the error is smaller than this. So, and you see that if n equals 4, this thing is smaller than 0.01. Right? So take the sum up to the fourth term. Okay, that turns out to be 1 minus 1 over 3 factorial. Okay, so I think that's probably the last thing. That's the last thing that is in the book that I want to show you. But let me close off with something that maybe you find entertaining. Okay, so so we've got these formulas, right? We've got e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus et cetera, et cetera. We've got the sine of x is x minus x cubed over 3 factorial plus x to the 4th over 5 factorial minus x to the 7th over 7 factorial plus minus et cetera. We've got this formula, cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus et cetera, et cetera. And we've got these formulas. What if I asked you, what if I asked you, what is the sine of I pi over 2? What is the sine of an imaginary number? Okay, suppose you're back in elementary school. You've learned, no, not elementary school. Suppose you're back in wherever you learned, trigonometry. I guess that was high school. Yeah, sorry. I forgot. It's a long time. Yeah. And somebody says, "What's the sine of I pi over 2?" And you're like, "What? That doesn't make any sense to me." Right? Because you're thinking of you're thinking of sine in terms of angles, right? And you say, what does this mean to have an imaginary angle, right? Okay. But now you have a way of talking about it, right? You say, well, here is the real line. It's sitting inside of a complex plane, right? Here's the complex plane, complex numbers, right? So you have this point would be 1 plus I, right? This is I here. This is 1, right? 1 plus I is this point in the complex plane. Okay. And you say, okay, well, in fact, if I take the power series expansion for E, at this point, the radius of convergence is actually infinite. Okay. That actually tells you that there is a radius of convergence, there's a disk of convergence in which that power series converges. The power series actually makes sense for complex numbers. In a disk that has that radius of convergence. That's why we call it the radius of convergence. Okay. And so these formulas actually all make sense if you're talking about complex numbers. Okay, this is actually how you define e to the complex number, sine of some complex number, cosine of some complex number. Okay. So for example, if I ask you, what is e to the I times some number theta? So theta maybe being some real number, e to the I theta. Well, that would be 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the 5 over 5 factorial plus I theta to the 6 over 6 factorial plus I theta to the 7 over 7 factorial, etc., etc., etc. Okay. But what's I squared? What's I squared? those of you who know complex numbers, I squared is negative 1, right? I squared is negative 1, right? I is the square root of negative 1. I squared is negative 1. I cubed would be negative 1 times I to the 4th would be negative I times I, but that's 1 again, right? Negative I times I, but that's 1 again. And then it starts repeating, right? So you get, the pattern is I, negative 1, negative I, 1, right? So we get this I, negative 1, negative I, and then 1 again, right? We get I, negative 1, negative I, and then just 1 again, etc., etc. Okay. Okay. So what? So what do you get? What do you see here? One point on the final.
Cosine.
0.
Cosine plus sine.
Hannah, go ahead.
Cosine plus sine.
Not cosine plus sine, but it's not exactly cosine plus sine.
X is I.
So you get 1 minus theta squared over 2 plus theta 4 minus theta 6, blah, blah, blah. Well, that is the cosine, right? Cosine of theta, right? What's the other thing you get?
Sine x.
I sine theta, right? I sine theta. E to the I theta is actually cosine theta, I sine theta. So this is a famous formula. It's called Euler's formula. E to the I theta equals cosine theta plus I sine theta. What is e to the I pi then? What is e to the I pi? What's cosine of pi? Negative 1. What's the sine of pi? 0. Okay, so e to the I pi equals negative 1. Kind of a bizarre conglomeration of famous numbers. Okay, that's it. Bye.